Hello and welcome dear students. Today we are going to discuss the topic remote sensing and GIS in watershed management. Watershed is a natural hydrological unit that collects, stores and drains precipitation through a network of streams to a common outlet. The watershed surrounded by ridges, hills are called as drainage divide depends on many factors. The drainage divide is responsible for draining surface runoff, water under the influence of slope, thereby creating basin topography. The large streams get its source of water from all the smaller streams, as all the surrounding water flows to accumulate in the large stream under the influence of either slope or gravity. The watershed consists of surface water like we have lakes, streams, reservoirs and wetlands, as well as all the underlying groundwater. The watershed is not simply the hydrological unit, but also socio-political ecological entity which plays crucial role in determining food, social and economical security and provides life support service to the rural people. Effective watershed management is essential for sustainable utilization of land and water resources, flood control, soil conservation, groundwater recharge and overall environmental sustainability. Traditional management approach relies heavily on field surveys and conventional maps. They are often time consuming, costly and limited in spatial coverage, especially for large and inaccessible areas. In this context, remote sensing and geographic information system have emerged as powerful and indispensable tool for modern watershed management. Remote sensing provides synoptic view, repetitive coverage and multispectral data that enables continuous monitoring of land, water, vegetation and terrain characteristics. However, GIS on the other hand allows complex spatial relationships within a watershed to be examined systematically. The integration of remote sensing and GIS enables accurate delineation of watershed and sub-watershed, extraction of drainage network and computation of morphometric parameters such as drainage density, stream frequency, basin shape and relief characteristics. However, these parameters are also crucial for understanding the hydrological behavior, runoff response, erosional susceptibility and flood potential. Moreover, satellite derived land use land cover information when combined with GIS based spatial analysis supports soil erosion assessment, groundwater potential mapping, watershed prioritization and planning of water conservation structures. Remote sensing and GIS also plays a crucial role in monitoring and evaluation of watershed development programs by analyzing temporal changes in vegetation cover, surface water availability and land degradation. With increasing challenges posed by climate change, population pressure and land use transformation, remote sensing and GIS approaches provide a scientific, cost effective and sustainable framework for integration of watershed management. In summary, the application of remote sensing and GIS has revolutionized watershed management by enabling data driven decision making and enhancing efficiency and supporting long term environmental sustainability and disaster risk reduction. Let us now discuss applications of remote sensing and GIS in watershed management. So, watershed delineation and boundary identification. So, watershed delineation is a process of identifying and mapping the spatial extent of a watershed. Accurate delineation of watershed boundaries is basically the foundation of watershed management. Hydrological modeling, flood analysis, soil conservation and water resource planning. Remote sensing and GIS aided watershed delineation has become more accurate, efficient and reproducible compared to traditional manual methods. Traditional methods used for watershed delineation are topographic maps, manual tracing along ridge lines and field survey, but it has too many limitations like it's time consuming, subjective and difficult in large or inaccessible areas. The introduction of remote sensing and GIS based watershed delineation need data from different space based sources like digital elevation model, that is DEM, satellite imageries and topographic maps. These are at times optional. The major steps in GIS watershed delineation are DEM preparation, sink identification and filling, flow direction analysis, flow accumulation analysis, stream network definition, pour point, that is outlet identification, watershed delineation and boundary verification and refinement. So, morphometric analysis of the watershed. The concept was pioneered by Houghton in 1945 and later refined by Streller, forming the foundation of modern quantitative geomorphology. Morphometric analysis is the quantitative evaluation of geometry and form of a watershed and its drainage network. It provides a numerical description of watershed characteristics, enabling a scientific understanding of hydrological behavior, runoff response, erosional potential, flood risk and groundwater conditions. With the development in remote sensing and GIS, morphometric analysis has become accurate, efficient and reproducible, making it a key tool in watershed management, hydrological modeling and disaster risk reduction. The morphometric analysis helps in understanding the drainage basin geometry and evolution, to evaluate runoff and flood characteristics, to assess soil erosion, to prioritize watershed for management and to support sustainable land and water resource planning. The remote sensing and GIS are extensively used to compute the linear parameters like stream order, stream length, bifurcation ratio, aerial parameters such as basin area, drainage density, stream frequency and relief parameters which are basin relief, relief ratio, etc. Another application of remote sensing is land use land cover mapping. So, land use is the human purpose or activity on that land, that is it could be agriculture, settlement, industry or transportation, and land cover presents the natural features which are forests, grasslands, water bodies and barren land. Land cover is what is there and land use is why it is there. So, they are distinct but related, as human use is land use often changes physical cover, that is land cover. Understanding land use land cover pattern and their change over time is essential for sustainable development, environmental management, watershed planning and disaster risk reduction. So, geospatial technologies provide powerful tools for mapping, monitoring, analyzing and managing land use, land cover in a cost effective and scientifically reliable manner. Satellite data offers synoptic and repetitive coverage, while GIS enables spatial analysis and integration with socio-economic and environmental data. Land use, land cover mapping and classification using satellite imageries is used to classify land into different categories. Using classification method like we have supervised classification, unsupervised classification and preparation of base maps for planning and management and identification of dominant land use type. Monitoring land use, land cover changes using multi-temporal satellite data over time helps or aids in identifying urban expansion, deforestation, agricultural intensification and wetland shrinkage for assessment of environmental degradation and support for sustainable land use policies. Urban and regional planning using mapping of built up area, road networks and open spaces support identification of urban sprawl and land conversion pattern from smart city planning, infrastructure development and zoning and land allocation. It helps in agricultural land assessment using identification of cropland, fallow land and cropping patterns. It also aids in monitoring crop growth, health and seasonal changes in crop area estimation, food security planning and irrigation management. The environmental impact assessment uses mostly land use land cover as baseline data for assessing impacts of development projects and monitoring post-project changes like mining, dam, roads and industrial areas. The other important application of land use land cover are watershed and natural resource management, disaster risk reduction, climate change studies and policy formulation and decision support. The fourth application of remote sensing is soil and erosional assessment, that is natural resources that support agriculture, ecosystem and human livelihood is soil. So, soil erosion is caused by water, wind, deforestation, improper land use and climatic variability. It at times lead to loss of fertile topsoil which reduces agricultural productivity, causes sedimentation of reservoirs, land degradation. Geospatial technology application plays a crucial role in assessing soil properties, mapping erosion prone areas and planning soil conservation measures in a scientific and cost effective manner. Satellite imageries are mostly used to identify different soil types and surface characteristics. Spectral signatures help in distinguishing soil texture, color, moisture and organic matter, which are highly important for classification of soil. It aids in assessing soil fertility and land capability, identify erosion prone zones, watershed prioritization after analyzing factors such as slope, land use and rainfall. Another types of remote sensing like microwave and thermal remote sensing data are at times used to estimate surface soil moisture. Active and passive sensors penetrate cloud cover and vegetation for soil moisture assessment, which had major role in irrigation planning, drought monitoring and crop productivity analysis. So, remote sensing helps track sediment transportation and deposition, while GIS model steady sediment yield and reservoir siltation for reservoir life assessment and watershed treatment planning. Remote sensing is used to assess the effectiveness of check dams, contour bands and vegetation barriers for monitoring the impact of soil conservation. It also aids in performance of watershed projects and adaptive management. GIS integrates soil, slope, rainfall, land use and erosion data and helps in prioritize areas for intervention for decision support and sustainable land management. Another one is runoff and flood modeling. That means the remote sensing has a major role for runoff and flood modeling, which is very essential component of hydrological analysis, watershed management and disaster risk reduction. Floods are among the most frequent and damaging natural hazard, causing loss of life, property and infrastructure. Remote sensing and GIS provides efficient tool for data acquisition, spatial analysis, simulation and visualization of runoff and flood processes, especially in large and ungauged basins. Geospatial technologies are at times used to delineate watershed and sub-watershed, and GIS tool helps to extract drainage networks, flow directions and flow accumulations for defining hydrological boundaries and establishing input parameters for runoff and flood models. The different satellite products like TRIM, GPM, INSAT provide spatial and temporal rainfall data mostly, which is useful in data scarce and ungauged regions for real-time rainfall monitoring and input for runoff and flood forecasting models. Remote sensing and GIS is used to estimate different watershed parameters like land use, land cover, soil and infiltration characteristics, runoff modeling using hydrological models, flood inundation mapping and floodplain zoning and hazard mapping. It helps to estimate runoff coefficients, determine infiltration capacity, estimate surface runoff volume and peak discharge, map flood extent and depth. The another application is in groundwater potential mapping. So, groundwater potential mapping is a process of identifying and delineating zones within a watershed that have good to poor groundwater occurrence and recharge potential. So, it is essential for sustainable water resource management, especially in regions facing water scarcity, over extraction and climate variability. Nowadays, remote sensing and GIS are extensively used to integrate multiple hydrological factors and produces groundwater potential zones maps at watershed, sub-watershed or basin scale. The main objective of groundwater potential map are to identify areas suitable for groundwater exploration and recharge, support well, sting and bore well planning, assists in watershed management and drought mitigation and promote sustainable groundwater use. The key factors controlling groundwater occurrence depends on a combination of geological, geomorphological, hydrological and land surface parameters. Geology and geomorphology always influence infiltration and groundwater storage. The geomorphic units like alluvial plains, valley fills, flood plains and peneplains favor the storage and infiltration. The high lineament density show increased permeability and groundwater movement, and intersection zones are ideal for groundwater development. The low drainage density represents high infiltration with good groundwater potential, while as high drainage density represents high runoff with poor groundwater potential. Gentle slopes represent more infiltration with high groundwater potential. However, steep slopes responsible for rapid runoff with low groundwater potential. Soil texture at times determines infiltration capacity in the area. Sandy and loamy soil shows high infiltration due to the presence of permeability, while as clayey soil depicts low infiltration. The methods used for groundwater potential mapping use remote sensing and GIS follows major steps like data collection from different satellite imageries, digital elevation models, geological and soil maps, and rainfall data. Preparation of thematic layers such as geology, geomorphology, lineament density, drainage density, slope, soil, and land use, land cover. Each thematic layer is assigned a weight based on its influence on groundwater occurrence, and individual classes within layers are ranked. For example, geomorphologically, high weight, slope, medium weight, and land use, moderate weight. So, GIS based weighted thematic layers are integrated using GIS tool, and composite groundwater potential index is generated. So, groundwater potential zones are classified into very good, good, moderate, poor, and very poor groundwater potential zones. Validation using well yield data, groundwater level data, and field observations has to be done. The another important application is planning of water conservation structures. Planning of water conservation structures aims to harvest rainwater, reduce surface runoff, enhance groundwater recharge, and control soil erosion within a watershed. So, traditional planning methods are time consuming and limited in spatial coverage. However, the remote sensing and GIS provides a scientific, efficient, and cost effective approach by integrating multiple spatial data sets for site selection, design, and monitoring of water conservation structures. The main objective are to identify suitable location for water harvesting and recharge structures and support sustainable watershed management. The water conservation structures planning using remote sensing and GIS include check dams, percolation tanks, farm ponds, gully plugs, nala bunds, contour bunds, and trenches. The thematic layers used in remote sensing and GIS are digital elevation model, drainage and stream order, map of the slope, soil, geology, geomorphology, land use, land cover, and rainfall and runoff data. The methodology for this planning include watershed delineation, preparation of thematic maps, identification of suitable zones using GIS overlay analysis, site selection for structures, design and capacity estimation, prioritization and implementation and monitoring. Remote sensing and GIS plays a crucial role in planning of water resources by various data sets. This scientific approach ensures optimal site selection, effective water harvesting, groundwater recharge, and sustainable watershed development. The another application of remote sensing in watershed is disaster management and climate resilience. Watershed management is again as a holistic approach to manage land, water, and vegetation within a drainage basin to achieve sustainable development. With increasing climate variability and extreme weather events such as floods, droughts, landslides and heat waves, integrating disaster management and climate resilience into watershed management has become essential. A climate resilient watershed reduces variability, enhances adaptive capacity and ensures long-term livelihood security. Disaster resilient watershed helps absorb shocks and recover fast. Role of watershed management in disaster management include flood risk reduction, drought mitigation, landslide and soil erosion control and disaster preparedness risk reduction. The climate resilience through watershed management focuses on enhancing adaptive capacity, ecosystem based adaptation, carbon sequestration and climate mitigation. The major role remote sensing and GIS plays are hazard mapping, climate vulnerability assessment and monitoring. Effectiveness of watershed interventions. Application of remote sensing and GIS. Now we will discuss a case study of Parvati Valley, Himachal Pradesh. The Parvati Valley, located in the Kullu district of Himachal Pradesh, is a Himalayan mountain watershed known for its fragile ecology, steep terrain, snow and glacier fed river system and growing anthropogenic pressures such as tourism, road construction and hydropower development. The case study highlights how remote sensing and GIS have been applied to understand and manage the Parvati Valley watershed. The study area has an altitude ranging around 1100 meter to over 5000 meter with temperate to alpine climate. The major rivers, namely Parvati River, a tributary of Beas River. The major environmental concerns in this area are landslides, slope instability, flash floods and cloudburst events, soil erosion, sedimentation, glacial retreat and changing slow melt pattern and pressure from tourism and infrastructure development. Remote sensing and GIS was used to delineate subwatershed, analyze land use land cover changes, identify erosion, flood and landslide prone zones, assess runoff and hydrological behavior and which supports sustainable watershed and disaster management planning. The Landsat and Sentinel 2 for land use land cover and vegetation analysis, Sentinel 1 SAR for flood and landslide monitoring under cloud cover, SRTM Amsterdam for terrain, slope and drainage analysis were used. The GIS and secondary data used are Survey of India topographic sheets, geological and soil map, rainfall and hydrological data, field observations for validation. The methodology applied for the study follows different steps. First, watershed delineation and drainage analysis using digital elevation model based hydrological modeling for delineation of the Parvati watershed and its sub watersheds. The drainage extraction and stream ordering helped in identify high energy streams. This aids in accurate watershed boundaries and identification of tributaries prone to flash floods. Another step, land use land cover mapping. The satellite image classification identified different land use classes like dense and sparse forest, agricultural land, snow and glacial cover, built up and tourism related infrastructure which aid in detection of forests, road expansion and settlement growth along valley floor. Slope and terrain analysis is the third step, analyzed using DEM derived slopes and aspect maps showed dominance of slopes to very steep slopes which are south facing with higher erosion susceptibility. The results show unstable terrain and support for land use regulation. Fourth step is soil erosion and sediment yield assessment. So, integration of slope, soil, rainfall and land use land cover layer in GIS helps for mapping of higher soil erosion zones, contributing to river sedimentation and downstream impacts. The fifth one is landslide susceptibility mapping using remote sensing data for mapping historical landslides and GIS based weighted overlay of slope, lithology, drainage proximity and land use. The preparation of landslide hazard zonation maps helps in disaster management strategies. Runoff and flood modeling. The satellite rainfall data combined with terrain, land cover parameters and GIS based runoff modeling for extreme rainfall and cloudburst scenarios are used for identification of flash flood prone river stretches and vulnerable settlements. Seventh one is groundwater and spring recharge zone mapping. The geomorphology, lineament density, slope and drainage density analysis has been utilized for identification of spring recharge zones supporting drinking water security and spring rejuvenation programs. The eighth one is climate change impact monitoring. So, multi-temporal satellite images used to assess the glacial retreat, snow cover variation and vegetation shift at higher altitudes for the evidence of climate induced change in hydrology and ecosystem dynamics. Thus, remote sensing and GIS based outputs had a scientific role in sustainable watershed management, supported by planning of soil and water conservation measures, regulation of land use in hazard prone areas, disaster risk reduction and early warning preparedness with climate resilient watershed planning. The Parvati Valley study clearly demonstrates that remote sensing and GIS are indispensable tool for managing fragile Himalayan watershed. These technologies enable accurate mapping, hazard assessment, hydrological modeling and monitoring of environmental changes, thereby supporting disaster risk reduction, climate resilience and sustainable watershed management. Thus, integrating remote sensing and GIS based scientific planning with community participation and local governance is essential for long-term susceptibility of such Himalayan catchments. This was all about today's lecture. Hope you have enjoyed it well. Thank you very much.